Hey, this is our last type of probability problem that we're going to talk about, and they are called OR problems. So these are situations where you're doing one event, but you have a choice. You can get this or this. So first vocab word that we need to set up is mutually exclusive events. If two events are mutually exclusive, it means that they cannot occur at the same time. Examples. I cannot pull a blue marble out of a bag and a yellow marble at the same time, assuming I'm only pulling one marble. Okay, so a marble cannot be both blue and yellow at the same time. I cannot roll a 1 and a 6 at the same time. That would be mutually exclusive events. Examples of things, let's see, if I cannot be registered to vote in 2 states at the same time. So those events would be mutually exclusive. If I'm a voter in New York or a voter in California, those are mutually exclusive. You cannot be both. Examples of things that are not mutually exclusive. Being a math major and being a female, you could be both. You could be a good cook and a good musician. Those two things could be could happen at the same time. So why this is important is because, again, just kind of like our AND problems with independent dependent events, the OR formula changes slightly depending on if the events are mutually exclusive or not. So our overarching rule for OR problems is that they are addition problems. So if I've got 2 events, I've got event A and event B, the way that I find the probability of A or B is I add them together. So that's the overarching operation that I want you to know for OR problems. AND is multiply, OR is adding. The problem lies in that sometimes when you're looking at all of A's events and all of B's events, they overlap. If they're not mutually exclusive, what happens is you've counted all of these events and all of these, and you've counted the overlap twice. So what you have to do is you have to subtract off the probability of A and B happening. Basically, what I call this is the overlap. Did you count anybody twice? Okay. I'll do a couple problems in several different formats, fractions, percentages, like we've done in the past, so you can get used to how these work. The first scenario I want to do is just a simple rolling of a die. If I'm going to roll a die, a 6-sided die, just normal, I want to know what's the probability that I roll a 5 or a 6. So I kind of set these up similar to the AND problems, where I decide how many choices there are and give myself a slot for each, and then I just put an addition sign in between rather than a multiplication. So I could get a 5 or a 6. Those are 2 different options, and I'm going to add them because it says OR. Then I'm going to subtract off the overlap. Now that may or may not happen. And in this case, because rolling a die is mutually exclusive, which means you cannot roll a 5 and a 6 simultaneously, there won't be any overlap. So sometimes this is not really part of the formula if the events are mutually exclusive. So let's take this one at a time. Probability of a 5, that's 1 out of 6. How many ways can it happen over your total? 1 out of 6. And the probability of getting a 6 is also 1 out of 6. No overlap. So I just add these. If you're not comfortable adding fractions, you can type this in just like this on your calculator. It'll do it for you. But if you're interested, when we add fractions, the denominators have to be the same. And the way we add them is we just add the tops. So 1 plus 1 is 2, and the denominator stays the same. So we're counting up how many pieces of, like, if a pizza is divided into 6 pieces, I take 1 and I take another 1. So that means I took 2 of the 6. That's kind of the idea of how addition works. That can reduce to 1/3, or if you divide it out on your calculator, it's 0.33. All of these are great. Both of these right here are great answers. So there's a 33% chance that you roll a 5 or a 6. Okay, let's take a look at cards. I know not everybody plays with cards, so I want to outline this here. The way that a standard deck of cards works is there's 52 cards. There's 13 hearts. There's 13 diamonds. There's 13 clubs, and there's 13 spades. These are all black cards, so that means there's 26 total blacks, and these are both red cards, so that means that there's 26 total reds. Now, each of these, we call these suits: hearts, diamonds, clubs, spades. Each of these suits has an ace, a 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. Okay, so there is one of all of these in hearts, one of all of these in diamonds, one of all of these in clubs, and one of all of these in spades, which means that each number, there's 4 of each number. So that means, like, if you look at all of these are all there's going to be 4 aces, 1 heart, 1 diamond, 1 club, 1 spade. There's going to be 4 2s. There's going to be 4 3s, and so forth all the way up. Okay. So the deck of cards is kind of a cool example because there is a lot of overlap. And so OR problems are interesting in this scenario. So let's just do a really simple one. Let's say, what's the probability that I deal you a heart or a diamond? So I'm doing 2 events. I mean, it's not 2 events. I have 2 choices. It's 1 event, but I'm just dealing 1 card. But I've got 2 choices. I'm going to add it and I'm going to subtract the overlap. So I kind of set myself up with my formula. I take 1 at a time. What's the probability that I draw a heart? So I go up here and I say, well, let's see, there's 13 hearts. So I've got 13 out of 52. What's the probability that I draw a diamond? Well, that's also 13 out of 52. And then what this is let me say it a different way. Instead of saying overlap, let's say it's both. Can I have both a heart and a diamond in the same card? So what I do is I take my 2 options and I say, what's the probability of having both of those? So the way that it's laid out, every card is either it's a heart or a diamond or club or spade. There's no cards that are both. So this is going to have no overlap. You cannot be a heart and a diamond at the same time. Okay. So you'd add these up. This is 26 out of 52. Reduce that or divide it out. If you divide it out, you get 0.5. Okay. New problem. What's the done that twice now. What's the probability that I draw a king or a heart? Okay. So again, I've got 2 options here. I can get a king or a heart. Sorry, my neighbor's using the saw next door. If you hear a little background noise. So king or a heart, or is plus. I've got two options here, and I'm going to subtract off a king and a heart. So any cards that are both. So let's start with king first. So here's all my kings. I've got one heart king, one diamond king, one club, and one spade. So I've got 4 total heart kings, 4 out of 52. Okay, how many hearts do I have? Well, here's all my hearts, ace through king here. I've got 13 of those. So 13 out of 52 hearts. Now, the question is there a card that is a king and a heart? And the answer is yes, because my heart cards are all dialed out right here. And this is the king of hearts. So I have one card that is a king and a heart, and that's what I'm subtracting off. That's my overlap. Okay, so this adds up to be 16 out of 52, which is 0.308. Okay, so that's kind of how the card situation works. Let's try one more. Let's do, what's the probability that I draw a red card or a 4? Okay, so again, I'm going to set it up the same way. I've got 2 options I'm adding, and I want to subtract off any cards that are red and 4s. So the red cards we have right here, there's 26 of them. The 4s, well, every suit has a 4. So there's going to be 4 of them, not because it's the number 4, but because there's 4 suits. And the question is, how many cards are both red and 4s? Well, there's a 4 of every suit. There is a 4 of hearts, a 4 of diamonds, 4 of clubs, and a 4 of spades. So 2 of them are red. So my overlap is going to be 2 out of 52. All right, so if we do that up, we get 28 out of 52, which is 0.538. Okay. So that is how you do the card problems. And then I want to show you what it looks like if we're in table form. Here's a table. Over here, we're looking at blood types. Okay, the blood types are right here: type O, type A, type B, AB, and then your total. And then your blood has something that is called an RH factor, and you either have it or you don't. So it's either positive or negative. And then this is how many of each of these there are. Okay, so let's find the probability that a certain blood that is chosen is either type O or type A. So my formula is going to say type O plus type A minus O and A. All right, so let's start with this. Type O is right here. There's 184 of those out of my total, which is 409. The type A is going to be 164 out of 409. And the question is, can you be type O and type A? And the way that it works is the answer is no, because you have to choose, you just have one type or another. Another way to tell in the charts is if you circle what you're looking for, if the circles don't overlap, then they're mutually exclusive. So this is 0. There's no overlap. And then you just go ahead and add the numbers. So 184 plus 164. I'm going to divide that by 409. And I'm getting 348 out of 409, which is 85%. Okay. Now let's look at something that's not mutually exclusive. So let's take a look at the probability of a donor being type B blood or Rh negative. So same setup, type B plus Rh negative minus both. So type B first, there's 45 type Bs. So 45 out of 409. Rh negative, that's all of these people right here. So this is going to be 65 out of 409. Now look, the question now is there anybody who has type B blood and is Rh negative? And the answer is yes. They're these people right here. These people have type B blood and are type negative. So what happened was you counted them in the B blood and in the Rh negative. Those 8 people got counted twice. So you have to subtract 8 out of 409. Okay. So what do we have? 45 plus 65 minus 8. We'll divide that by 409. And I get 102 out of 409 is 25%, 0.25. Okay. So that's how you do the OR problems. Now, a question I get often is, what about replacement with these? Replacement is not an issue with OR problems because we're actually only doing one event. In all of these problems, I'm picking one person. I just have a choice of what kind of person I'm choosing, this one or this one. So replacement's not an issue like it is with an and. An and is unique because we're having multiple tasks. I'm going to pick multiple marbles, multiple people, multiple cards. And so then the question is, are they getting put back after I choose them? But with an or, I'm just choosing one person. I just have choices. So replacement's not an issue there. Okay, good luck, and I will talk to you later.